Hello, everybody. Here we are, 4.3. I'm recording in Miss Caddy's classroom on my spare block, and I can hear a video through the wall. So hopefully, hopefully, can't hear that in the video. But here we go. 4.3 rational exponents. A bit of review. A rational number, remember from grade 9, is a ratio of two numbers, and so it can be shown as a fraction or a decimal. 2/3. The decimal needs to be terminating, so it needs to end, or it needs to repeat in a predictable way. So classic irrational numbers are pi, the square root of 2, square root of 5. Actually, the square root of any non-perfect square is an irrational number. And radical form is when we have the square root sign. So very common one, square root, second square root or cubed root. These are in radical form. And a reminder, for adding and subtracting fractions, you need a common denominator. So if we want to add a half to, a fourth, we need to have the same number on the bottom first. So we need to change the way a half looks by making it the same denominator. So we can change a half into 2/4. It's still the same value, but now we have a common denominator. I don't know why I'm getting a little... When I do the equal sign, it looks like a little F. There we go. We can add those two. And same for subtracting. You need a common denominator. And if we're multiplying fractions, you just multiply the tops, multiply the bottom. So 1 times 1, there it is again. 1 times 1 is 1. And 2 times 4 is 8. I'm not going to go over, if you remember dividing fractions, it's keep, change, flip. But for our purposes, I don't think we're really doing any dividing fractions, but you can review that if you'd like. Always good to know. So let's go over today. We've dealt with our, we know this one classic 9 squared, 9 times 9, that equals 81. And we've been dealing with integral exponents, so negative exponents. We know that this flips our base. So this is the same as, so we currently have a 9/1. And if we have a negative exponent, we can flip our base. So now 1/9 to a positive 2. We can distribute the 2 inside to the 1 and to the 9. And we get... there we go, 1/81. So you'll notice as you go, remember when I showed the diagram, we had 2 to the 1 and 2 to the 2 and 2 to the 3. We had there 2, 4, 8. If we're going this way, we're timesing by 2. Okay, if we're going in a positive exponent, we're multiplying by 2. And if we're going this way, say we got 2 to the 1, and then 2 to the 0, and then 2 to the -1. So we got 2, then we got 1, then we got 1/2. But go this way, we're dividing by 2. So that might be a way to remember that. And now with our rational exponents, we're dealing with fraction or decimal exponents. The answer to 9 to the half is 3. And why is this? Okay, so there's a few ways I think that I would like to try to explain this to you. And the first one is to reimagine how we can represent 9. We can represent 9 as 3 squared. So just bear with me for a second. 3 squared is 9. It's the same. It's just a different format. And so I've now just substituted our 3 squared for the 9. And if you imagine I put that to the half. So if I have 3 squared to the power of a half, and now let's use the exponent laws to solve this. I'm going to have 3 to the 2 times. Remember, if you have power of powers, you can multiply that. Times 1/2. I'm still in red. There we go. Times 1/2. And so this 2 is a 2/1. If we multiply this, what do we get? 3 to the power of 2/2, or 3 to the power of 1. Okay, that's one way to think about it. Another way to think about it is this is kind of, if you think about the answer is 3, if we have 9 to the half, we're asking ourselves, what times itself would give us 9 to the 1? If we had 9 to the half times 9 to the half, here we have the same base. It's being multiplied, so we could add those exponents. 9 to the half plus a half, and a half plus a half will give us 9 to the 1. So it's kind of, in a way, a fancy way of showing a square root. And so that's the next part that we need, that I want to talk to you about or show you, is a way to represent radical exponent as rational exponent, in radical form. So when a power has a whole number for its base and a fraction for its exponent, it can be rewritten as a radical. And remember, the roots are on the bottom. Think about the roots of a tree. They're on the bottom of the tree. So this one here is going to be your root, and this one here in the top is going to be your exponent. So a way that we can rewrite 16 to the half is to show it 2 as our root and 16 to the power of 1. I like to put the 1 on the outside. I think it's easiest in my mind to kind of solve this part first and then deal with the exponent after. If we have, this is now asking us for the square root of 16, which I know to be 4. 4 to the power of 1 is just 4. Here we have 8 to the third. So we can use 3 as our root and 8 to the 1. So we're asking ourselves, what times itself 3 times equals 8, or what is a cube root of 8? I know that to be 2 to the power of 1, which is just 2. And I want to point out, right, this is saying that if we had 8 to the third times, which is 2, times 8 to the third, let me show it a little bit better, times 8 to the third times 8 to the third. So a third plus a third plus a third, which is 8 to 3/3, which is 8 to the 1. So if you had this, remember this is equal to 2, this is equal to 2, this is equal to 2, you'd also get 8. And I want to show you one more. Oh, maybe I shouldn't erase that if you wanted to write it down. My bad. But let me show you just another one, just for the sake of it, to show you what it looks like. So 8 to the 2/3 if you don't have a 1 as a numerator. So still we have 3 as our root, the 8, and then it's squared afterwards. The cube root of 8 is 2, and then it's 2 squared. 2 squared is 4. So that's very handy. I don't know if it's in our textbook. I'm not sure why, but I think that's a very kind of like handy and maybe even kind of easy way of looking at this. So let's solve a few by converting to a radical. So remember, the bottom one is our root. The top is the exponent. And so we have 4, 16. I'm going to use my calculator for this. This one right here, 4, 16. So what times itself 4 times is going to give us 16? It's 2. Here we go. And here again, this is the 3 is going to be our root. The 4 is going to be our exponent. So cubed root 27 to the power 4. The cube root of 27, not 24. What times itself 3 times gives us 27? That's 3 to the power 4. And 3 to the power 4 is 81. And another, you could think about it if you could rewrite this in a way that maybe makes it easier to reduce. You could think about it as a cubed root. What's another way to show 27? Another way to show 27 is as 3 cubed. And remember, taking the square root or taking the cube root and cubing are inverse operations, so those cancel each other out. We're left with the 3. So that's why that works. So let's do a few, and we just need to remember, I know it looks kind of, freaky or scary at the beginning, but let's just apply our exponent laws like we're used to. So now we have the same base, they're being multiplied, so we can add the exponents. So we got x to the half plus 7 over 2. And luckily, they have the same denominator, so we can just add the tops. X to the power of 1 plus 7 is 8 over 2. And we can simplify that further to x to the power of 4. Okay, let's do the next one. This one's a little trickier. And remember, we can only combine our m's. They have the same base, so we just kind of bring the 3 over, and m to the 4 plus 1 over 4. And you might be tempted here just to add the tops, but we need the same denominator. So don't forget this is over 1. And 1 and 4 are not the same thing, so we need to change this 4 over 1 so that it has a 4 on the bottom. So let's, over here, times top and bottom by 4. And we get 3 to the m, 16 over 4 plus 1 over 4. And then we can add the tops, 3 to the m. 16 plus 1 is 17 over 4. Okay, this one we have some decimals. I want to deal with inside before I multiply by the half. So we have the same base, it's being multiplied, we can add the exponents. So x to the power 1.5 should be a 0.5 plus 2.5. Oh, my pen is, there we go. There we go, that's all to the 0.5. So now we got x 1.5 plus 2.5 is 4, and that's to the 0.5. And now we can multiply inside. So 4 times a half is going to give us x to the 2. Let's look at the next one. This one can be tricky. I think it's good to reduce inside the brackets first. We have 5 over 20, which we can reduce to 1 over 4. 5 goes into 5 once, and 5 goes into 24 times. And then we have an x to the 3 over an x to the 1. We can minus those exponents. We're left with x squared on top. And this is all to the half. And now we can distribute this half inside. We're going to apply it to the x, and we're going to apply it to the quarter. So what it's going to look like essentially is that we're going to have a 1 to the half over a 4 to the half and an x squared times a half. And I think it's best at this point to convert it to the radical form. So we're going to have, remember the 2 is our root. So square root of 1 over, I'm going to do the same to this x squared, and I'll show you why. So times the second root to the x squared over square root of 4. And now we can reduce this. What's the square root of 1? It's just 1. And this now we have the square root of x squared. We have inverse operations. Those can cancel each other out. We're left with an x over the square root of 4, which is 2. So you can show that as 1x over 2. You could also just show it as x over 2. Okay, and our last one, I know there's no reducing we can do inside, so let's distribute our 3 inside to each of these. We've got x to the 2 over 3 times 3, and a 3 over 1, times a y 4 over 3 times 3 over 1. So let's see if we can cross reduce. Looks like we can. We have a 3 there, and so when you're cross reducing, you look diagonally to see if you have any of the same numbers or any of the same factors. 3 can go into 3 once, and 3 can go into 3 once. Again, here, 3 can go into 3 once, and 3 can go into 3 once. And we're left with x, 2 times 1 is 2, and 1 times 1 is 1, so I'll just leave it at that. And y, 4 times 1 is 4, over 1 times 1 is 1. So there you have it. There's your final answer. Thank you so much. I will give you the textbook questions I'd like you to work on.